Okay, so next speaker is Erika Bertolini, and she's going to talk about quasi-topological mass generation for 3D linearized gravity. Yeah. Okay. Okay. Thank you. First of all, thanks to the organizers for this very nice conference and for giving me the opportunity to share with all of you one of my latest research. So I've been working on higher rank gauge theories lately, and this made me investigate a bit more on some aspects of modified gravity and linearized gravity, especially. Why are people interested in massive gravity? So it is known from observation that the universe is in an accelerated expansion, and this was first explained in terms of the cosmological constant giving some kind of negative pressure and interpreted therefore as a dark energy. This thus predicted from observation a certain value of the cosmological constant, but this is in disagreement with some quantum field theoretical predictions. Some other ways for justifying this accelerated expansion can be found, for instance, in the context of FOR's theories. But lately, people have been interested also even more in massive gravity theories, because from developments in the observation of gravitational waves from LIGO and Virgo, for instance, an upper bound, a non-zero upper bound on the mass of the graviton has been defined. That's a very small bound, but it's non-zero, and this gave a push into the investigation of massive gravity theory, which, through the existence of a possible long-range potential, could explain also this accelerated expansion. So that's why massive gravity. So in my talk, I'm going to work on 3 space-time dimensions. So why is it interesting in the context of massive theory? So it has a lot of peculiarities, and it's been used as a toy model for testing new physics in a lot of context, and especially also in some massive gravity theory, as I will show you in a few slides. And that's because in 3 space-time dimension, gravity is renormalizable, which is the consequence of being a topological theory, and therefore it has no local degrees of freedom, no propagating massless gravitons, and therefore no gravitational waves in the massless case. But some surprising things appear with the massive introduction. But so how do one see that there is no gravitational wave? So the linearized gravity action in 3 space-time dimension is the usual one, doesn't change in any way. It's still invariant under diffeomorphism. And so by considering the customary covariant gauge, the harmonic gauge, one can find through the equations of motion, again, the usual wave equation, so nothing changes here. However, in the further studying this on the TT gauge, one can see that this gives enough constraints to completely switch off, let's say, the gauge field. So then this means that the theory has no propagating degrees of freedom in this case. But this will change when a massive term is introduced. And this has been done at least twice in the past. So there are 2 main models for massive gravity in 3 dimensions. And the first one was developed in 1982 by Deza, Jakiv, and Templeton, and it's called topological massive gravity. And the second one was developed in 2009 by Berkshire, Form, and Townsend, and it's known as new massive gravities. So in the first case, it is described by the following action term. So the standard, more or less, Einstein-Hilbert term is coupled to a higher derivative term, which is the following one. So I'm saying more or less because there is actually a minus sign in front of the Einstein-Hilbert term. That's relevant, and it's necessary to get positive energy states. And this higher derivative term has a massive coefficient with negative dimension, and it's parity violating and generates mass through Maxwell-Chern Simons-like topological mass generation, which was actually described in the same paper. By computing the linearized equations, one can see that the Klein-Gordon equation for the D'Alembertian of the gauge field in the TT gauge gives a mass for the graviton, and the number of degrees of freedom can be identified by decomposing the gauge field, as I will show you in a few slides. And this shows that this model is describing 1 degree of freedom, one massive degree of freedom related to the transverse part of the gauge field, and it's a spin 2. On the other hand, the new massive gravity model is similar. So we have, again, the Einstein-Hilbert term with negative sign, and a higher derivative term in terms of the Ricci tensor and scalar. This time the theory is parity preserving, and the mass generation mechanism is more like a Fierz-Pauli mass term, let's say. We can compare the two. One is written in terms of the just metric perturbation, the other with Ricci tensor, but they look alike a bit. And in the same way as the Fierz-Pauli term is tuned in order to avoid ghost-like states, this 3/8 factor is there for the same purpose, so in order to avoid ghost states. And here again, the mass appears as in the Klein-Gordon equation for the Einstein tensor. This additional equation is the one responsible for removing the ghost-like part. So this model instead describes 2 propagating degrees of massive degrees of freedom of spin 2 and mass mu(n). So the 2 models share some similarities and some differences. For instance, in the topological massive gravity case, this exists only in 3 space-time dimensions. That's because it's of the presence of the Levy-Civitas tensor, while new massive gravity a priori exists in any dimension, even though I think there are some issues in the higher dimensions. The first one is parity violating, and the other one is parity preserving. And this is connected to the fact that one has 1 degree of freedom, massive degree of freedom, and the other 2. But there are also some other open, let's say, aspects, open questions that are related to the fact that the massive part has a coefficient with negative mass dimensions, which then implies that the massless limit is actually reached only for the mass going to infinity, which actually gives not just the pure, let's say, usual Einstein-Hilbert term, but the same with a minus sign, which was said to be wrong sign in the new massive gravity paper. Also, it's in some sense in disagreement with the physical situation, because the mass of the graviton, as I show you at the beginning, it's actually very tiny. So we should get the linearized gravity term for a very small mass, so for mu going to 0 instead of infinite. And these are actually effective theories, since we can build infinite invariant terms. So this last open points, let's say, motivated the work with my collaborators that was actually recently published. And so I have to underline that a difference here is that we are going to work only on the linearized gravity part. So the nonlinear version will be studied in the future. On the contrary, in the topological massive gravity and new massive gravity, they started from the nonlinear terms. So we started with some requirements for the theory. So we want to have a well-defined massless limit that gives us the linearized gravity term with proper sign. We want propagators to be well-defined in the massless limit and to have massive poles, and no physical ghosts should appear in the theory. This has to be compatible with power counting, and the degrees of freedom, the massive degrees of freedom should be related to the spin 2 components, since we want a theory of massive gravity. And this should be in agreement with one of the two models that I've been describing, because we don't want to have a huge plethora of very different theory ones. We want some agreements. So that was the proposal. So we have our action that's composed of the linearized gravity term plus a massive contribution. And the massive contribution is given by this Chern-Simons-like term. So it is linear in the derivative. It's not topological because we have summation over the indices. And the whole theory is actually not invariant under the complete set of diffeomorphism symmetry, but only under a subset of it, which is called longitudinal diffeomorphism. A side comment: this symmetry is related to a class of theories known as covariant fracton theory, which I've been working for some time as well. So just that side, we can already see that this model satisfies two of the requirements. So it has a good massless limit, which gives us the linearized gravity term with proper sign, and it's compatible with power counting. So now we want to go on. We want to treat this as a gauge theory. And therefore, since our gauge transformation has a scalar gauge parameter, we impose a scalar gauge fixing. We do this by introducing this gauge fixing term to the total action. And now we compute the propagator and see if we have also the other points being satisfied. So sadly, it turns out that this doesn't work. So some of the coefficient has a pole on the mass. So this propagator doesn't have any good massless limit. But not all hopes are lost, because actually we should have treated this as a usual gauge theory, a massive one, where the mass breaks the gauge invariance, and our real symmetry is related to the diffeomorphism. So we want to consider the theory with a vector gauge fixing, so the usual harmonic one with the following gauge fixing term, therefore. One interesting thing is that the symmetry is broken by the mass term, but actually it is broken in a controlled way, because we can see that its variation on the gauge fixing actually vanishes. And this is an interesting sign, because it's telling us that there is probably a hidden symmetry of the whole gauge fixed action, so some kind of PRS symmetry, as I will show you at the end. So now we can go on and study the whole theory with the new gauge fixing term and look at the propagator, which now we're happy we have a good result. And we see that the coefficients of the propagator has a massless limit, a non-divergent massless limit, and it's giving us the propagator of linearized gravity when the mass goes to 0. And it's also telling us that the gauge field has a mass that's related to m, to the mass parameter. Additionally, we can see that there's no physical ghost or tachyonic poles appearing, and we can say something more if we look at the propagators on another basis, which is known as the Barn-Rietveld basis. This has a nice feature of being written in terms of spin projectors for a symmetric rank 2 tensor, which means in particular we can look for the poles related to the P2, so the spin 2 part. And that's the result. So we see that the massive pole is actually related only to the P2 contribution, which is telling us that the theory has a massive spin 2 degrees of freedom. But we can go on and even counting the degrees of freedom, as I was anticipating at the beginning. One can do this as it was done in the paper by Zurchikov and Templeton. And so we can decompose the gauge field in terms of irreducible representations of the rotation group, and then further on in terms of transverse, longitudinal, and solenoidal part. This satisfies the following relations. And then we can therefore look at the action in terms of this decomposition. And we see that some multipliers appear that we can integrate out, and they gives us some constraint for our theory, which gives us in the end the following action term. So this depends on only one scalar, and there is and the equations of motion are telling us that this is the one related to the Klein-Gordon equation, to the massive Klein-Gordon equation. So the massive propagating degree of freedom is 1, and it is this box of U. But what is this physically? So we can do the same decomposition on the Ricci tensor, for instance, and see that in the harmonic gauge, which is the one we are considering and the one that restore the breaking of the gauge symmetry, we see that this box of U, the D'Alembertian, is related to the transverse part of the spatial Ricci tensor. Therefore, it is the transverse part of the spatial Ricci tensor which is related to the massive Klein-Gordon equation, which is again in agreement with the result of Zurchikov and Templeton for the topological massive gravity. Finally, we can, as a proper gauge fixing procedure, one needs to consider the BRS transformation, as I was mentioning. And so we need to introduce some ghost and anti-ghost fields and their transformation. And we still have the usual diffeomorphism transformation in terms of the ghost field. And this is a symmetry of the gauge fixed action, of the massless gauge fixed action. But it is broken by the massive contribution, by the massive term. However, we've seen that there is a controlled symmetry breaking. I mentioned that that was a sign of a new symmetry, and in fact, we can define a new modified BRS-like operator through this additional term, and this is indeed a symmetry of the whole massive gauge fixed action. And not just this, because this new BRS operator is not nilpotent anymore. However, we are exchanging this nilpotency with the existence of a new operator delta, which is again a symmetry of the action. And it gives us a new algebraic structure for the theory, which is actually similar to a known one for topological Schwartz-like field theories. And this is another reason why we're calling this model quasi-topological. But what's important here is that we have a symmetry related to this Ward operators that is uniquely identifying this our theory. So I can just summarize here that we finally had a three-dimensional massive model that satisfied the requirements. So it has a good massless limits. It's giving us the linearized gravity term with proper sign. The propagators is well defined with the good gauge fixing term. There is no unphysical ghost appearing. It's power counting compatible, and the degrees of freedom, the degree of freedom, which is 1, is massive, and it's related to the spin-2 component of the gauge field. But not just this, we also got an additional surprising result. So we found that there is a BRS-like symmetry, BRS-like structure that's uniquely identifying this theory. So what to do next? Well, first of all, we want to identify the nonlinear theory, so to connect to the, let's say, logical structure of the other models. This then would help us to get to the 4-dimensional extension, if there exists one, and how it looks like, and further investigating the the new extended symmetry, which could give us some hints for the 4-dimensional extension, for instance. And I wanted to thank you all. Questions? Can you make some comments about that? Thank you. Well, I could give a whole talk about this, but yeah, I don't have the time. Yeah, it's just interesting because, yeah, so fractals are related to this. So I asked because at some point in the talk, she mentioned about the connection with fractals, and I asked if she could comment a bit more on that. So yeah, fractals appears as a gauge theory invariant under this symmetry. So one can define a full set of actions that are typically Maxwell-like, but refer to higher ranks gauge fields, typically ranked to symmetric gauge fields. And so yeah, linearized gravity can be considered as a particular case of it, which is additionally invariant under the diffeomorphism symmetry. But so fractals are quasi-particles, so are more related to the condensed matter side, and they describe quasi-particle with limited mobility and some kind of Maxwell-like structure, therefore higher rank gauge fields. So and this action term is also related, can be studied on its own, like a Chern-Simons-like term, and this on its own can be associated to some covariant fractal theories. So it seems like there is some intertwine there. That's relating linearized gravity and these models. But yeah, this would require a long talk. Thanks for the question. Thanks.
So if you consider a Wilbein formulation with Lorentz connection and 3-bind, there's a natural term which you can write, which is just product of epsilon E omega, which would be nonlinear. I'm not sure, maybe it vanishes, but it looks like nonlinear generalization of this term, which will have.
Yeah, that's another aspect that we were thinking of studying in the future. I was talking to a collaborator about this recently. Yeah. Yeah, that's